So, good evening, everyone. I hope I'm audible and my screen is also fully visible. So, in in so this is actually tutorial 5 of the linear algebra course, the NPTEL course linear algebra. So let's begin the tutorial session for today's tutorial session. So tutorial 5 linear algebra NPTEL. Mm, I hope this is NOC 26 MA 100 and today is 21st August. So, so as like to the previous tutorial, so today also discuss some problem, uh, and if you have any problem, you can tell me. I'll try to discuss those problems. Those problems can be from the previous assignments. Those problems can be from the any course material. Those problem can be um, can be any material which are problems related to the linear algebra course. This course. So you can ask me if I can try to solve those problems. So if you um, so so if you have any problem, you can stop me and you can ask me. Otherwise, I will try to do some problems which I prepared, which few I prepared, and I will try to discuss those problems. So if you have, so I hope I'm clear, audible, right, and my screen is also visible. So so this is the first problem. So let's see what this problem says. This is the problem which says to find the true and false of these few problems. Okay, so what this problem says that let question is that mark whether the following statements are true or false. Justify your answer. Okay, first question: the vectors 1 1 1, something like that, 1 2 1 2, and like one forms an basis of r to the power n or not. Okay, so let me recall some few facts. Recall, we have discussed what is the linearly independentness, all these things. Let V be a vector space. V be a vector space over a field K. Then for any subset S of V, linear span of uh, linear span, which I written LS, which is actually summation of all Ci alpha I, where alpha I is coming from the set S and Ci coming from the field K, and here I is running from 1 to some n for some n natural number. Okay, so this is called linear span, and this is a subspace. This is a subspace. Now, a subset is said to be generating set for the vector space V if there exists set S for which the linear span is the full vector space V. Then S is said to be generating set for V if linear span of S is actually exactly the vector space V, and if the set if the elements in set are linearly independent, if the elements in S are linearly independent, then S is said to be basis of the vector space V. Now, S can have finite number of elements, S can have infinite number of elements. So if S has finite number of elements, then the set linearly independent means that finite number of set element is linearly independent. If S has infinite number of elements, then in that situation, linearly independent means choose any finite number of elements subset. That finite number of elements subset has to be linearly independent. This is what it is meant by linearly independentness of an infinite subset. Okay. Now the point is that if we have a basis, the interesting fact is that you can write any element. Suppose let S is equals to some element alpha and alpha to alpha n is a basis of the vector space V over the field F. Then for any element V in capital V, you can write V as summation of alpha I, summation of Ci alpha I equals to n for some unique choice of scalar C1, C2, Cn. What does that mean? Unique choice? Unique choice means if you have any other choice of Ci dash alpha I for which that is also V, then that will imply that all Ci has to be Ci dash corresponding to each I. Okay, all Ci has to be equals to Ci dash. This is what it is mean by unique choice. Okay. Now, this is what it is. So basically, what is basis is doing? Basis is something like something skeleton. Okay, you can choose that is the smallest collection, and taking linear combination of that smallest collection, you will get the full space. That's what it is called the basis. Okay. For example, if you take R2, in that case, that is the collection of all A, B, such that A and B are coming from real number. In that case, basis is 1, 0 and 0, 1. This is the basis. Why this is basis? Choose any element A, B. You can write A, comma B in this form. So that's why you take any element coming from the vector space R2 is actually the linear combination of these elements. Okay, so that's why this is basis. This is something like the smallest test which generates the vector space itself. Okay, so this is what it is basis. Okay, for example, if you take the space of all polynomials with coefficients over real, with real coefficients, then the set 1 x square all the way, this is infinite set, is the basis, is the basis. Okay, so this is what it is mean by basis. Okay, so let us once again, let's take the problem once again. So this was the problem. So we'll so basis and the number of, okay, before going to this one, so number of elements for a finite dimensional, the number of elements, the number or cardinality basically, let V be a vector space. Cardinality of the basis, okay, two fact actually. If we consider, I mean, then question is that here is also, for example, in this situation, this is the basis I have said. But if you consider 1, 1 and 1, 0, that is again basis. But these two are not same set, right? So then question is, for a vector space, there can be more than one number of set of bases, right? So, but what is the connection between them? First of all, one basis can be written in terms of other, that's separate point. But the number of elements in a basis has to be same. If the number of element in basis, number of, okay, so for a vector space V, for a vector space V, the number of elements in a basis can be finite or infinite. For any two bases of a vector space, for any two bases of a vector space will have same number of elements that can be finite or infinite, elements that can be finite or infinite. finite or infinite. If it is infinite, then any two bases will have infinite number of any two bases can have infinite number of elements, and if you have finite number of, then any two bases can have finite number of bases. If the basis, if if the basis of the vector space has, if the basis of the vector space has finite number of elements, numbers of elements, then V is the vector space. If the basis V has the finite number of elements, then V is said to be finite dimensional vector space. Otherwise, it is infinite dimensional vector space. Okay, dimensional vector space. So, dimension of the vector space R2 over the field R, that is equals to 2. Whatever basis you choose, that doesn't matter. It will have always two dimension. Okay, this is the dimension. So let me come to this question. Then, okay, so here is a question. Question asks, what are the which of these are true or false? So first question is the vectors 1 1 1. This is what it is. Let's take first vector is e1, that is 1 1 1. This is what it is. Second vector is e2 equals to 1 comma 2 comma 1 comma 1, something like that. And third vector is like 1 comma 1 comma n. Forms a basis or not? Basis of Rn or not, right? The question is whether this is E2 and this is, let's take En, okay? Okay, so the vectors 1 1 1, first position 1, next to second position 2, and n position n, that's what it is, right? Whether E1, E2, all the way En forms a basis or not? The answer is yes. First of all, whether this is linearly, so what is I need to check? I have to check that every vector in R to the power n can be written as the linear combination of vectors of this. And first of all, one thing, note that R to the power n is a finite dimensional vector space with dimension n, and one of the basis is that is consisting 1 comma 0 comma 0. Next one is 0 comma 1 comma 0, that is all the way. Last one will be 0 comma 0 comma 1. This is what it is, the basis in the R to the power n. Now the question is, this is basis, and so that's why the dimension of R to the power n is actually equals to n. So now, as I have said, any basis can have n number of linearly independent elements of the vector space V, because dimension is fixed. Dimension cannot be changed. So that's why any basis will have only finite number of n number of elements. So to show whether this is forms a basis or not, if I can prove only that this is linearly independent, then we are done. Okay. If this is linearly independent, then we are done. So here is the point. Linearly independent and linearly dependent means, what is the means? That linearly independent or dependent means that the set will be linearly independent if one cannot be written in terms of the linear combination of other. Dependent means there exists one vector which can be written as the linear combination of other. The question is, if all these vectors are linearly independent, then note that E1 all the way En are linearly independent, that is, one, there does not exist any vector, does not exist any vector that can be written as linear combination of some other vectors. Okay, so that is equivalent to the fact that determinant of the matrix 1 comma 1 comma 1 1 comma 2 comma 1 1 1 3 all the way 1 comma n, this determinant is not equals to 0. Linearly independent means this is equivalent. Okay, so but whether this determinant is equals to 0 or not, first of all, we know for if we have a matrix whether determinant 0 or not, that I can do it by changing by row reduction process. If you do the row reduction process, and we can um, try to find the determinant of the new matrix, whether that is non-zero or not, that can be decided. So if you do the if you look like that ri dash is equals to ri minus r1 for all I greater than equals to 2, then what will you have? You have 1 1 1 all the way. Next one will be like 0 1 0 0 0 something like that, 0 0 1 like this way. Okay, no, ri dash will be ri minus ri minus 1. No, I know, not like that, not like that. R1. Okay, for all I greater than equals to 0. Next one will be 2. All the way 0, and in this one, next one will be n minus 1. So this is the matrix, okay? This is the row reduction matrix. Now, what is the determinant of this matrix? If you take this is the A matrix, so what is the requirement? Requirement is that then determinant of if A equals to, then determinant of A not equals to 0. So what is the determinant of this matrix? So if I take A tilde, so determinant of A tilde is nothing but 1, 1, 2, n minus 1, that is n minus 1 whole factorial, and that is not equal to 0 if n is greater than equals to 1, right? If n is equals to 1, then is also not equals to 0 for n greater than equals to 0, because this is factorial. So 0 factorial is 1. So that thus the set E1 all the way En is linearly independent. This is first fact. And consists in number of elements, that is uh, equal to the dimension of the vector space V, and this gives the set E1 E2 En is a basis of the vector space V over R. Okay, basis of the vector space R to the power n over R. So that is the first. So 1 is true. 1 is true. So this is the first question which asks that whether this forms a basis or not, whether this set of vectors forms a basis or not. The second is that in every finite field K, there exists an unique prime number P and a subfield K dash of cardinality P. Okay, so let's take K as a finite field. What is the question is saying? In every finite field K, there exists a unique prime number P and a unique subfield K dash of cardinality P. So question is, in every finite field K, there exists a unique prime number P and a unique subfield K, unique subfield K prime of unique subfield K prime of this statement, unique subfield K prime of cardinality. Cardinality means number of entries, and characteristics means that's the smallest. There is a unique prime number P, that what is called the character. No, not said anything. Okay, okay. So we'll do this now. So what is given here? Given here is that we have a field, a finite field. K is a finite field. Okay. So let's take the characteristics values of the field K is M. Now give a map phi from the integer z to k by phi of M is going to be M dot 1 of k. 1 of k is the identity of multiplicative identity of the field K. identity of the field K. Okay, this is what it is. Multiplicative identity of the field K. This is the scalar times multiplicative. This is what it is. So the question is, this is a ring homomorphism. Okay, so Z is a ring. Is a ring. This is a ring homomorphism. But we don't need all these things. Let me directly go to the point. This is a ring homomorphism. Okay, this is a ring and this is a field. That means P is a ring homomorphism. But as K is finite, but Z is not finite, then phi cannot be injective. Then phi is not injective. So as phi is not injective, then kernel of phi is an ideal, non-zero ideal of Z. But Z is in principal ideal domain. Z is in principal ideal domain. So every ideal in Z which will be scalar, some prime multiple of the, that is, there exists some p, prime number p, prime p, such that kernel of phi is actually equals to p of Z. Okay, that means that gives phi of p, that is equals to p dot 1 of k, that has to be 0, right? Now, so we got the prime number p first of all, but we have to find the unique subfield k dash of cardinality p. Now let k dash is equals to, if now if, okay, we have find a number p, we have not said that. Okay, prime number, if we say, okay, this will be prime. In fact, a prime, why p needs to be p needs to be prime, p has to be prime. Let me check. P has to be prime in principal ideal domain. Here it is, in this situation there exists an, I mean, there it is prime, as if p is not prime, that is ab, for some 1 less than a less than b, not less than 1, strictly less than a, strictly less than b, strictly less than strictly less than p, then p of 1k is equals to 0. That gives a1k dot b1k is equals to 0. But Z is principal, Z is an integral domain. You can, here you can, so here I can write more generally. Z is an integral domain, but Z is an integral domain. Moreover, any, this is an integral domain. That means principal ideal domain. Okay, Z is a principal ideal domain. Everything is clear. So every ideal must be generated by some element. Z is an principal ideal domain. Then kernel of phi is equals to pz for some p belongs to Z. Moreover, p is a prime. Why p is prime? That's what I am here explaining. As this is a principal ideal domain, so this product of two elements is 0. That implies either a dot 1k is equals to 0 or b dot 1k is equals to 0. But that says, that contradicts the fact that that kernel of phi is equals to pz, because that sending every element which is multiples of p to 0. But here it is, what we are getting, there exists at least element a and b whose multiplicity is less than p, which is less than p, but that is also sending to 0. But that's not possible. This is phi of a equals to 0, or phi of b is equals to 0. That's not possible. What that contradicts the fact that says that what it says that p is a prime. P is a prime. Next is that P prime is obtained, but next is that let us consider the field K dash that is equals to consisting like phi 1, phi 2 all the way phi of phi 0. Let's start from phi 0. K dash is equals to phi 0, phi 1 all the way phi of P minus 1, P minus 1. This is a field, is a subring of P elements where this subring is in K. Okay. Moreover, this is in subfield, you can check, and this is isomorphic to, and this is isomorphic to Z mod PZ, that is the field ZP cardinality. So that's why K dash is a field. I have not been in details in this situation because this question is not that much. I believe is not that much relevant to the linear algebra. So that's why I have tried to be. So that's why, and cardinality of K dash is actually equals to cardinality of the K dash, that is the P. So this, that is the statement 2 is true. Next, go to the next statement. So what is the next statement says? Let P be a monic polynomial of degree n. Okay. The solution space V is equals to all those funds, functions, polynomials basically, such that PDP, okay, all those functions, continuous functions, n differentiable continuous function, complex valued continuous function, PD of y equals to 0 of differentiable equations, PD equals to 0 is a C vector space of dimension n. So what is the questions? Let's P be n. Question is, let P be n, let P a complex polynomial be a monic polynomial of degree degree monic polynomial of degree, what is the question? Monic polynomial of degree n. This is what it is given, first of all. Another is that the space, solution space, which is giving V is equals to all those functions. These are complex valued n times continuously differentiable functions belongs to C. This is continuous symbol, this is complex valued, and this is n time differentiable, complex differentiable. C is such that P of D y is equal to 0. Okay, this is what it is given. Of differentiable equations, P d y equals to 0 is a C vector space, so that V is a complex vector space. So whether this is complex vector space or not. First of all, space of all continuously different n times continuously differentiable complex valued function is itself a vector space. Now, if you take two elements y1 and y2, which is coming from the vector space V, then what will happen? That P of d y1 is equals to 0, and again P of d y2 is equals to 0. That is different. PD is something I'm going to define. What is PD? So, so if you take C is any scalar coming from the field complex number, then you can look at PD of y1 plus cy2, that is again 0. Why this is? So what is mean by PD first of all? What is PD? Okay. If P, here it P says the monic polynomial. If P of X is equals to something like that, A naught plus A1x plus all the way A n minus 1 x to the power n minus 1 plus x to the power n. As it is monic polynomial, the highest degree coefficient of the highest degree term has to be constant 1. Okay, so this is what it is, the monic polynomial. So what is mean by PD? If I consider dn is equals to dk by dx to the power k, the kth derivative. This is what it is. Then P of D is nothing but A naught identity plus A1 D. Okay, this is what it is. D dx plus A2 D square dx square plus all the way plus A n minus 1 D to the power n minus 1 dx to the power n minus 1 plus next one is D to the power n dx to the power n. Okay, so 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 from here you can look at carefully that thus the set V is a vector space. V is a complex vector space. Now the question is not only the complex vector space, so that V is a finite dimensional vector space. Now the next part of the question is that finite dimensional vector space. I think that was the question. Question was vector space of dimension n. This is the point where we need to check dimension n. So this is the point where we need to do some work. Otherwise, it is not much difficult. So why it has dimension n? So what are the elements in there? So clearly, this 1 x, I'm going to define why all these terms will be there. X minus 1. All these terms are contained in the vector space V. Why? This is contained in the vector space V. Because all these terms are contained in the vector. Because clearly, note that if you take constant function 1 and if you try to find a PD of 1, what will happen? It will be 0 at each stage, and at this point it will be, this is constant, at this point it will be a naught only, constant function 1, it is a naught only. So what I want? I want that 1 is there. That's what I want, right? PD y is equals to 0. Oh, sorry, 1 is not there, I think. 1 is not there. Then x to the power n will be there. Okay. X to the power n. So if I take ax, what will happen? It will be, just a minute, little bit. Okay, so another way we can prove. This is the vector. This is, let's give the, this is the, what this vector space is there. Now let us define a map phi from the vector space V to the complex number Cn, which sends every element y to y of 0, y dashed 0, all the way y nth derivative, n minus 1 derivative at the point 0. Then clearly this is a linear map. Then phi is a linear map. Why that is linear map? That because if you take phi of y1 plus y2 scalar times of y2, then you will automatically get that y1 plus y2 at the point 0, y1 plus y2 dashed at the point 0, all the way y1 plus y2 whole at nth minus 1 derivative at the point 0, and which you can separate it like y1 of 0, y1 dashed of 0, all the way y1 to n minus 1 derivative at the point 0 plus y2 at the point 0, y2 dashed at the point 0, y2 dashed n minus 1 at the point 0. Okay, so this is what it is possible. So that's why phi is linear map. Phi is a linear map. Now due to the existential existence and uniqueness of the OD, the existence uniqueness of ordinary differential equations, what it says But what you can do is that ordinary the existence and uniqueness of OD is what it gives, that there exist. Achha. Here I am looking for each, that for every C belongs to Cn, there exists there exists exactly one vector y such that phi of y is equals to C. So phi is surjective, and okay, why, what is mean by this? There exists existence and uniqueness of the ODs. The existence of uniqueness of ODs, what it means, let me explain clearly. What it means, the suppose we are giving the map phi sending y to y of 0, y dashed of 0 all the way y dashed of y to the power n minus 1 at the point 0. Now if I am seeking like that c1 c2 c1 c2 cn, that means we are seeking a system of linear equation such that we are searching a y such that y 0 is equals to c1, y dash 0 is equals to c2, all the way y n minus 1 dash 0 is equals to cn. We have given all these things, then we have to find the y. Okay, that's not very difficult to finding. Okay, we can get a solution. Basically we can get a solution of the unique partial differential equation, that p of dy is equals to 0. From there is a unique solution of this equation under the condition there is an unique solution of there is an unique solution of y with this all this condition. So just a minute, by the existence and uniqueness theorem for linear ODEs with constant coefficient. Okay, so this gives phi is actually surjective, but now phi is injective. If I want to get phi is injective, if all these are equals to okay, so here one needs to check phi is injective, then phi is bijective and linear, then what will have, then we'll have the dimension of then phi is an isomorphism, then phi is an isomorphism that gives dimension of the vector space V is same with dimension of C to the power n as a complex vector space. That gives dimension of which is actually n, that gives dimension of V is equals to n. So what you need to prove is that phi is injective. Why phi is injective? Because if phi of y is equals to some phi of y1 is equals to phi of y2, that gives that y1 0 all the way y1 dashed 0 all the way y1 into n minus 1 0 of all n minus 1 differentiable function, then y to n minus 1 0 for to nth differentiable function function. Okay, in that situation, just 1 second. Okay, sorry, we don't need all these things. We don't need all these things. We just need to do from here. From here, we'll existence gives there is an two thing, the existence and uniqueness. Okay, here is the thing, existence and uniqueness. Existence and uniqueness. This gives the onto of phi, and this gives the 1 property of phi. So, so this gives bijectiveness directly. So this gives the dimension all equals to n. So this will hold. So that means the last option, that was the option 3, is also true. Yeah, this question is not that much pleasant for me at least. So let me go to some other questions. So what is this problem says? So what is this? For which pair A and B in field, K is a field, let's take K is a field and V is equals to AB and V dash is equals to B. So the question is for which pair, uh, question is for form a basis for the K vector space of K2. Okay. So if it is basis, then it has to be linearly independent. So that means determinant has to be non-equal to 0. So but here K is something like that uh, field, but here K is not mentioned anything for which pair. So we have to mention. Um, okay. So let K is a field, K be a field, and K2 is a vector space, is a vector space over the field K. In fact, it is always two-dimensional vector space. Let's take V is equals to AB and V dash is equals to BA. Then question is, um, question is when they form a basis. When form a basis. So this will form a basis if C1 AB plus C2 BA is equals to 0 implies, should imply C1 is equals to 0, C2 equals to 0. This is what it is we should have. Okay, this is what it is we should have. So what is means that C1A plus C2B, another is that C1B plus C2A, this is automatically equals to 0 0. So this will give C1A plus C2B is equals to 0 and C1B plus C2A is equals to 0. So now here what it is saying that we have only one choice of C1 C2 to satisfy these two properties, that is C1 equals to 0, C2 equals to 0. Then what is the choice of alpha and beta can be? Okay, so one easy way is that like you can make it like the equation like A B If it is in real value, then it will be easy for AB, but I hope it is considering as the real value. Otherwise, this addition and all these things does not make sense. So AB, B, A, this determinant of this has to be equals to not equals to 0. Then then this system of homogeneous, so basically you can write it as A, B, B, A. This is a system of homogeneous cylinder equation. C1, C2 is equals to 0, 0. Consider C1 and C2 as a variable. So that means this is right now A of X is equals to 0, where A is equals to AB and BA, and X is actually equals to C1, C2. Now for a system of homogeneous equations, for its n by n matrices, that in that situation, zero solution is the only solution only when determinant is not zero. If determinant is non-zero, then we can make A inverse, then we can multiply A inverse both sides, and you will get 0 is the solution, and you will not get any other solution. So that's why determinant has to be not equal to 0. But determinant has to be not equal to 0 when A square minus B square is not equal to 0. That means A square is not equal to B square. This is what it is, the solution. That is either so AB comma BA, this is a basis of K2 of the K2 field, and over the field K2 of the vector space B, K2 over the field K, if and only if either A is equals to minus B or A is equals to B. These are the two situations in which situation this will form a vector basis. Okay, so this is the solution to this question. What are the solution to the other question? What are the other questions? That's the determine the coordinates of the vectors I0, 1 plus I. This is with respect to the basis. Okay, this is very interesting. So let me tell you one thing then. Determine the coordinates of the vectors this and this with respect to the basis v1 is equal to this and v2 is equal to this of the C vector space C square, where I denotes the imaginary number. Okay. So what are the tasks? Task is that we have to find the basis. We have to find I0, 1 plus I comma 0, and 1 plus I comma minus 2 plus 3I in terms of in terms of 1 plus I or 1 plus I. Okay, we have to prove. So what is the one main point I want to point out, that if you have a vector space V, let V be a finite dimensional vector space with two bases. One is suppose alpha and alpha to alpha n. So that means it has n number of elements. That means the dimension is n. Another is that and beta 1, beta 2 all the way beta n. So these are two bases. Then one can be written in terms of other. That's for sure. Because why? Then one basis, elements in one basis can be written in terms of other basis. That means if I write alpha I, that can be written as something like Pij beta j summation of j is equals to 1 to n. So that means in this way you can write alpha 1, alpha 2, alpha n. This can be written as P1 1 beta 1 plus P1 2 beta 2 plus P1 n beta n, and in this way P2 1 beta 1 plus P2 2 1 2 2 2 2 beta 2 all the way P2n beta n, and all the way Pn1 beta 1 plus Pn2 beta 2 plus all the way Pnn beta n. Okay, so that means this can be written as the matrix Pij with column vector beta 1 to beta n. So that means one basis can be written in terms of other basis, but through a matrix. This matrix is called the basis change matrix. interestingly, if you take two bases like this and this, in that case the basis change matrix is always invertible. Okay, and that inverse, if you multiply this side, then you can get that the beta 1 beta 2 beta n plus 1 in terms of there. Okay, so this fact is of course not relevant to here, but here given basis is that 1 plus I comma I, 1 comma 1 plus I. Here 1 plus I comma I and 1 comma 1 plus I. These are the two bases, right? 1 comma 1 plus I, 1 plus I comma I, and I have to written in terms of, I have to write I comma 0 and 1 plus I comma minus 2 plus 3I. This is what it is. I have to write this and this in terms of this. Okay, so let's write I comma 0. Let's take this is equals to a of 1 plus I comma I plus b of 1 comma 1 plus I, and let's take 1 plus I comma minus 2 plus 3I. This can be written as a 1 plus I comma I, b, sorry, this is I'm writing two separate c, and d 1 comma 1 plus I. Okay, so this can be written as a of 1 plus I plus b comma ai plus b of 1 plus I. This is what it is, and here I can write it will be like c of 1 plus I plus d comma ci plus d 1 plus I. This is what it is. So what we'll get a of 1 plus I plus b is equals to I. This is the first place, and second place is that ai plus b of 1 plus I is equals to 0. Okay, note that here a and b both can be complex number, because here we are trying to find the here a and b both can be complex number. Why here a and b both can be complex number? Because we are in complex field and we are trying to find these two elements in terms of these two. This is what it is. That means this is a basis of our C2, and this is also basis of C2. We are trying to find one basis in terms of other. So coefficient can be complex number. There is no problem with being coefficient from the complex number. Okay, and but I'll come to the point how I have to find AB, right? That's the main point, right? So here what we can write, okay, let me check then. AI plus A plus B is equals to I, and here I have AI plus B 1 plus I is equals to 0. So here I will get AI is equals to I. Okay, so here I will get AI plus B plus A, which is equals to I. Here I will also get AI plus B plus BI is equals to 0. So if I compare AI plus B, then I will get AI plus B is actually I minus 1, which is equals to AI plus B, which is equals to minus BI. That gives, I'm trying to do quickly, but you can do the general form is that you have to find the matrix and you have to find the inverse. I'll go to that situation, but let me first check whether through this also it is possible or not. First of all, let me check whether I have written all the notations correctly or not. Otherwise, everything will be in absurd situation. This in terms of ABs, and this in terms of this. Okay, so let's do some differently. So this way, I think this will be easier, but okay, let's go to the standard process. This way, whatever I'm trying to do, that will also be easier, but but that will be too risky. So let's take this is v1 and this is v2. This is v1 and this is v2. I want to write. I want to find this is any vector, any c, any vector c1 comma c2 that can be written in terms of some x v1 plus y v2. This is what it is. So what is x of v1? 1 plus I comma I plus y of 1 comma 1 plus I, and that will give y plus x of 1 plus I. Plus this is what it is. I have also initially trying to do, but let's instead of taking, I am trying to get in general, and later I will decide what is c1 c2. What is x and y in terms of c1 c2? Okay, so that means what we get two equation right now. One is y plus x into 1 plus I, which is equal to c1. Another is that y of 1 plus I plus xi is equals to c2. So I want to find x and y. So basically I want to find the matrix. So if I write x and y way, this will be written as 1 I plus x plus y is equals to c1. Ix plus 1 plus Iy is equals to c2. So I want to write it in terms of matrix. What it will be? It will be like I 1 plus I, this one with xy, this is equals to c1 c2. So let's check, this is the matrix. Let's take this is the matrix M. So what is the determinant of M? Determinant of M is equals to 1 plus I square minus 1, that will be like 1 square plus I square, which is plus 2i minus 1. I square is equals to minus 1, so 1 1 cancel out, it will be 2i minus 1. If I am not correct, I have calculated M, determinant of M is equals to, yeah, no, I think there is an issue. This is I, not minus. This is I. This is minus I. So this will be minus I. This will be I. Okay. That is not equal to 0. So M is invertible. M is invertible. So what is the M inverse? M inverse equals to what you know? M inverse equals to determinant 1 by determinant of adjoint. Okay. Adjoint of M by determinant of M is I 1 by I. Okay. And what is the adjoint of this matrix? Adjoint of this matrix is 1 plus I, and this is the position, and this will be 1 plus I corresponding to 1, that will be I minus I. So minus I will place here, and corresponding to I, this will be minus 1, this will be 1 plus I. I hope I am correct. So this will be like 1 by, this is the inverse. Okay, this is the inverse. So if I so if I use this I here, then what I'll get? 1 plus I by I. Next one is minus 1. This will be minus 1 by I. 1 plus I by I. So what is 1 plus I by I? First of all, this is equals to, if I multiply I both above and below, this will be I square. This will be like I minus I square, that is minus 1, and I. So that is I minus 1 by minus 1, that will be 1 minus I. So this will be like 1 minus I, and this can be written I square. So this will be I minus 1, 1 minus I. This is the matrix. So what is C1, C2? C1, C2 is nothing but, what is X1, X2? What is X1, X2 corresponding to C1, C2? X1, X2 is nothing but M inverse C1, C2. What is M inverse? This is I, 1 minus 1, 1 minus I, and the C1, C2. Now C1, C2. Now corresponding to what is the C1, C2? So we have two C1, C2. One choice is that I comma 0. So what I have to write C I comma 0. This is if I take C1, C2. Then what will be the X and Y? What will be the X and Y? X and Y will be 1 minus I. This will be I. This will be minus 1, 1 minus I, and this will be like I comma 0. So this will be, first product will be 1 minus I into I, that is I minus I square, that is I plus 1, and another thing is that minus I. This is the thing. So that means first vector I comma 0 can be written as I plus 1 into V1 plus minus I into V2. And similarly, if I take other vector. What was the other vector? Other vector was 1 plus I minus 2 plus 3I. 1 plus I minus 2 plus 3I. This is as C1, C2. Then what is the corresponding x and y? That will be 1 plus 1 minus I minus 1, 1 minus I, and if we multiply the C1, C2, that is 1 plus I and 2 plus 3I. And if you, I will not do this because this is not much relevant. You can do that will be. I hope that in that situation x and y will be, in the situation x will be equals to, that means the first coordinate, that will be equals to minus 1 minus 2y, and y will be equals to, okay, I'll do it, okay, not a problem, 4i. So let's check whether this is correct. So what is the, that is the first, and this is the first one, right? So this will be 1 plus I, 1 minus I, that is 1 minus I square plus I into minus 2 plus 3i. So this will be 1 minus I square minus 1 and plus 1. So this will be 2 plus 2 minus 2i plus 3i square. So 3i square is actually minus 3. So minus 2i minus 1. Okay, this is what it is. And the second one is 1, then minus 1 minus I plus 1 minus I into minus 2 plus 3i, and this will be, I hope there will not be any problem, 4i. Okay, so this is what it is. The way, so how to solve. So this is what it is. What we have done actually, we have tried to solve this problem. Whenever you have two vector and we want to calculate these two vector with respect to writing these two vector in terms of other two vectors. This is what it is we are doing. We are trying to write these two vector in terms of these two vector v1, v2. Okay. I hope this is clear. If you have any doubt, you can let me know. I know the previous question was not that much. I'm not that good in the previous questions, but I hope this question is okay. If you have any doubt, you can let me know. Otherwise, I'm going to the next problem. Okay, just 1 second only, few seconds only. Okay, so what is this question says? Let K be a finite field of cardinality Q. Okay, prove that K vector space V of dimension n has exactly Q to the power n elements. Okay, this is sometimes interesting because this type of question sometimes appears in the CSI net exam and sometimes in JAM as well. So what this question says, let K be a finite field of cardinality Q. Let V be a vector space of dimension n. Okay, let V1 all the way Vn is a basis of the vector space V. Okay, over the field K. That's of course over the field K. Then what are the elements? Question is, what are general elements in V? That is some scalar multiple of scalar linear combination of the elements, that is C1 Ci Vi I equals to 1 to n, and where this Ci can come, Ci can belong in the field K. Now so basically what we have a basis v1 v2 vn, okay, and you have scalar c1 ci I can choose from K. Now for the each position, so let's assume like corresponding to v1 the scalar is c1, corresponding to v2 the scalar position is c2, all the way corresponding to vn the scalar position is cn. Now point is that here c1 can be any element of the field K, here c2 can be any element of the field K, here cn can be any element of the field K. But question is the cardinality of K is actually Q. That means for the first one, what are the number of choices? That Q. Corresponding to each choice in the first position of C1, what are the number of choice in the second position? That is again Q. Corresponding to the second position, the third position will again be Q, and all the way this will be Q, and here is total n number of Q appears. So that's why what will happen, the cardinality will be Qn. So basically what is happening, so total number of elements in the vector space V is actually Q to the power n. Now question is, okay, someone can ask whether it is possible, let's take C1, C2, Cn one choice, another choice C1, C2, C1 dash, C2 dash, C2 another choice, and we take C1 V1 all the way plus Cn Vn. Here it is C1 dash V1 plus all the way Cn dash Vn dash. The question is whether can they be equal when we know these two factors are not equal. When we know these two are not equal, mean at least one coordinate they are not equal. This is what it is I mean. If these two are not equal, that means at least one coordinate they are not equal. Whether it is possible, they will form the linear combination of the same vector. Whether this is possible, the answer is no. Why the answer is no? Because V I V1 V2 Vn is a basis. So if these two equal, then what I can write? I can write Ci minus Ci dash whole into Vi I equals to 1 to n, and this is equals to 0. But Vi are basis. That means if we have a linear combination of an basis elements equals to 0, then the coefficients in that linear combination necessarily has to be 0, all of them. Okay, so that means that will give Ci minus Ci dash is equals to 0 for all I is equals to 1 to till the point n. So that means Ci has to be equals to Ci dash for all of them, for all I equals to 1 to. So that means if we choose C1, C2, Cn different from, I mean, if you take two pair of the two n tuples, basically two n tuples, these are called n tuples. If we choose two n tuples of different two n tuples of the elements coming from the field F, where at least one of the coordinate is different, in that situation we will get a different vector. So that's why there will not be any problem to, like, here will be q, I mean q times q times q times a after up to n times if we product, then that number of element in the vector space. Okay. Okay, so this is what it is. I hope it is also clear. So number of elements. So basically, question is the dimension of the exactly number of elements. This is what it is. So that's the number of elements, not the dimension. Has exactly q1 to the power elements. So that means we are getting distinct elements for the distinct tuples of the field elements. Okay, so note that in this q to the power n number of elements, 0 is also one of the member. Okay. So what is the second question? Second question says that let n be a natural number and a is a real number and b is the. So here is a point. We should here add this. I think there is a mistake in this. So dimension of f is less than n, still less than n. Prove that V is a vector space over R of dimension n. This is what it is the question. So V is the vector space. What V is giving? V is giving f mod x minus a to the power n, such that f is a polynomial. It is rational polynomial or just real polynomial. F is real x and coming from this is polynomial. Okay, these are the definitions. So fx is Rx. Polynomials with real coefficient. Okay, so here it is taken that f is element coming from Rx and degree of f is actually n, degree of f is less than n. So this type of polynomials where you are taking ratio of two polynomials, this is an element inside Rx. So first of all, understand the difference of the notation. This is the space of all rational polynomials. Rational functions. This is no longer polynomial. Rational functions is nothing but the ratio of two polynomials, and each of them are coming from the each of them are polynomials with the coefficients coming from the real number. This is what it is, okay? And Rx is the space of all polynomials. That means polynomials with the coefficients coming from real number. So, what is the question? Question is, n is belongs to, and a is a fixed number. Prove that V is a vector space of R, vector space over R of dimension n. Okay. So V is I have to prove that V is a vector space of dimension n. Okay. So here if we consider, okay, first of all, f is a polynomial of degree less than n. So let's take f is equals to, so if I take, these are the polynomial 1 x minus a square, 1 by x minus a square all the way, 1 by x minus l to the power n. This is, why these elements are in there? Because this, first of all, check that this is in V. Why this is in V? Because f can be any polynomial of degree less than equals to n. How one will get this corresponding to the choice of f is equals to x minus a whole to the power n minus 1. How one will get x minus a square, the corresponding to the choice of f is equals to x minus a whole to the power n minus 2. All the way, how one will get x minus a to the power n corresponding to the choice f is equals to 1. Here degree of f is degree less than n. That means the degree can be maximum n minus 1. So you can look at carefully that we are utilizing all of the polynomial and these elements are contained in there. First of all, this is the situation. Second is that this is linear combination. I mean, this is a, second is that, claim is that, so this, if I take, this is the script A set, A is a generating set of V. Why? A is a generating set of V. Why generating set of V? Any element in V is given by something like that, polynomial f of x of degree less than equals to 1 and x minus a whole to the power n, that can be written as something like a naught plus a1x plus all the way an x to the power a n. Okay, so here is the point. So another claim, I am not proving this, x minus constant x minus a square all the way x minus a to the power n is a basis of the space of all polynomials p n x of degree n. So that's why I can write any polynomial, then any f, so here it is, I will do it x to the power n minus 1, here it is n minus 1. So any f belongs to p n minus 1 x can be written as f is equals to a naught plus a1 x minus a plus all the way a n minus 1 x to the power a minus n minus 1. We can write this way. So any element, if any element look like this way, so if I replace this element here, what I will get? A naught plus a1 x minus a plus a n minus 1 x minus a n minus 1, and all the way this is x minus a to the power n, and this will be give a naught by x to the power n plus a1 by x minus a to the power n minus 1, all the way it will be a n minus 1 by x minus a to the power n. So basically this is, so this is the claim is correct. The script A, this is the set, this set is generating set of the space V. Now if I can prove that this is linearly independent, then we are done. So now claim script A is linearly independent over the field real number. So if summation of Ci, or basically you can write C1 by x minus a, C2 by x minus a square plus all the way Cn by x minus a l to the power n is equals to 0, then I have to prove all the c1, c2, cn has to be 0. How one can get this? Look at carefully. We can write it as look like this way: c1 x minus a whole to the power n minus 1, c2 x minus a whole to the power n minus 2, all the way cn is equals to 0. But note that I have said this 1 x minus a square x minus a to the power n minus 1. This itself is the basis of the space of all polynomials of degree n minus 1. And so that's why if we write this is equals to 0, then we should have c1 is equals to c2 all the way is equals to cn is equals to 0. As once again I am mentioning, as 1 x minus a square all the way x minus a to the power n minus 1 is a basis of Pn minus 1. Okay, so that's done. So that means the set script a is equals to 1 by x minus a square all the way x minus a to the power n is a basis of the vector space. What is the vector space? Vector space V. That means dimension of V is equals to n. Okay, this is what it is. So I hope this is also clear. If there is any doubt, you can let me know. I'll try to explain once again. And if any other doubt which you are encountering throughout this course, you can still ask me. I'll try to explain those things. And I hope my audio and video, everything is clear and my screen is also clear. If there is any problem in that side, also you can let me know through the chat section or through just opening your mic and speaking through your mic. That is also possible to us. So if you have any doubt, you can let me know. So otherwise, I'll go to the next problem. You can even stop me in that anytime and you can ask me your doubt if you have any. Okay, so before solution of this problem, let me do one more problem. Then I'll come to this problem. Okay, so okay, let's start this, and whatever the result is required, I will mention. Actually, one of the result for to solve this problem is required, which is coming from the assignment problem of this week. So that's why I will not be solve. I will not solve that problem, but I will use that problem as the result, and I will try to solve this problem. Okay. So what this problem says, let K be a field and A naught, A1, A2, An are the distinct elements. Okay, okay, just a minute. No, I think. Oh no, not this problem. Sorry. Let me go to that problem. Just a minute. Oh. So this is the problem. So I will not solve here two problems. I will solve the only one problem. So this problem I will solve. I'll solve this one only. Okay, so what is this problem says? Let f naught, f1, f2, fn are polynomials in the space of all polynomials. So let Pn the space of polynomials degree n, okay? And let's take f naught, f1, fn are all elements come from Pn, and let's take a naught, a1 all the way an are given, okay? These are also given with the property fi of ai is equals to 0, not equals to 0, and fi aj is equals to 0 for all I not equals to j. Okay. Then f naught, f1, fn are basis of p to the power n. That's the point. So why that is a basis? First of all, they has to be linearly independent. That's first choice. And second is that they should span the space. That's the second choice. Okay. Then the second fact. Then we can say that okay, that is a basis. Otherwise, at least we have to do this. That's the thing. So let's check linearly independentness. So let me write it clearly. Claim claim is that f naught f1 fn is a basis of what, the space Pn. So how I will do? So first of all, so that's basis means you have to do check two things. One is linearly independentness and another is linearly dependentness. So check linearly independentness. So let's take Ci I equals to 0 to n is equals to 0. Okay, then I have to say all Ci is equals to 0. Now this is a polynomial. This is a polynomial. So now if we evaluate, let's take this is a polynomial capital F. Okay. Now f of ai, what will happen? F of ai is equals to ci of f of aj. Let's take f of aj. Ci fi aj, where I is equals to running from 0 to n. But fi is, I mean, first suppose aj is fixed. J is fixed right now. Okay. So now if I take I is equals to 0, but j is not equals to 0, in that situation f of 0 aj has to be 0. If I take by this property, then fi aj is equals to 0 if I not equals to 0, but fi ai is not equals to 0. That means in this sum, only when I is equals to j, in that situation the term will survive, otherwise it will be 0. This is equals to cj and fj aj. Okay. Now if I this is a zero polynomial, so what will have, what will have 0 is equals to 0. So that means you choose any, I mean, f at any point it is 0, right? F is a zero polynomial. F is the zero polynomial that will send every element to 0 irrespective of whatever it is there or not. So but so that what we obtain cj of fj alpha j, that is equals to 0, but it is given that fj alpha j is not equals to 0, that says cj is equals to 0. That says cj not equals to 0, and this is true for every j coming from 0 to 1. So that means the set f naught, f1 all the way fn is linearly independent. This is clear. Now let's come to the point of basis, spanning set. Okay, so that's the question which is related to the next one. If we consider g any polynomial in Pn that can be written in terms of, then we can say that okay, that's the spanning set, because so that's basically, so let's write this way. Let so claim f naught f1 fn is a spanning set or generating set of the vector space V. Sorry, here it is Pn. Here the notation is used Pn. Okay. Why that's happening? Because let G be another polynomial in the Pn. We have already know that there is some, we are prescribed some value. These are coming from real number. So we have G naught, G function, G is a polynomial. So we have value G of A naught, all these things. So let's take the polynomial G of A naught by F of A naught, F naught, plus G of A1 by F of A1 f naught plus all the way g of an by f of an f, sorry, this is f1, this is fn. So this is g. My claim is this is the function g. Why this is the function g? Let's take this is a polynomial. Consider the polynomial. Here is an interesting result. Consider the polynomial. Consider the below polynomial or following polynomial. Okay, this is the polynomial. Let's take this is something like some notation g tilde, because I am constructing in terms of g tilde. Then claim is g tilde is equals to g as a polynomial. Okay, as a polynomial function. As a polynomial function. Why this is happening? So that's what it is you have to prove. So what we know? Here is a standard result we will use. What is the standard result we will use? If P is a polynomial of degree n and non-zero, then what is the number of roots of the polynomial can have? Number of distinct or different, distinct, repetitive, whatever it is. If P is a polynomial, non-zero polynomial of degree n, then P can have maximum n number of roots. That can be distinct, that can be repetitive, that's not the point. Maximum distinct roots, what one can consider. If here it is said distinct, yeah, it is distinct. There, suppose there are this such that there are this distinct. Here there needs to be distinct. Okay, distinct is needed, otherwise it is not possible. If P is a non-zero polynomial, degree n, then it can have at max n distinct roots. This is what it is, or zeros. This is called roots or zeros. Zeros. So that means if you consider a polynomial of degree n and that have more than n number of distinct roots, that means the polynomial has to be 0. That's what it is. So if P is a degree 3, so if P is a polynomial of degree n and have more than n distinct root, then P has to be necessarily identically 0. That means all the coefficient will also be 0, identically 0 polynomial. That's sending every element to 0, that's what it is. But the point is that here, so if you consider g tilde minus g, okay, I'll this one, okay, let's g tilde minus g, and if you evaluate this at the point ai, what will happen? If you write g tilde of g and at the point ai, then what will happen? G of a naught by f of a naught, f naught ai, plus g of a1, f of a1 and f1 of, sorry, this is f1 of a1. I think I have written little problematic statement. F naught f1, yeah, f naught f1 fn, yeah, this there has to be also f naught f1 fn. Okay, so this is what it is. It will continue till g of an by fn of an and fn ai. Okay, what we know, all this summation, whenever the position is ith position, only in that situation fi will survive, right? In all other situation, all terms will be 0, right? This is f1 ai and this is fn ai. Okay, so that means here it is automatically becoming g of ai by fi of ai into fi of ai, that is equals to g of ai. Okay, sorry, this is g of, okay, so let okay, we can g tilde, so basically this is g tilde at the point ai look like this way, so that will turns out to be ultimately g of ai, right? So that is for all I is equals to 0, 1 to n. Then clearly here is the point. Then g tilde minus g is again a polynomial, as g and g tilde have degree more at most n of, so that means g tilde minus g will also have more than degree more at most n, polynomial of degree less than less than equal n. That says if the polynomial g tilde minus g have degree less than equal n, and g tilde minus g at the point ai is equals to 0 for all I equals to 0, 1 to n, that means it has, that is g tilde minus g admits n plus 1 distinct roots. So that means this polynomial g tilde minus g has to be equal to 0 polynomial is 0 polynomial. So this is established that g is equals to g of a naught, f naught, a naught, f1, g of a1, f1, a1, this is f naught, f1 plus all the way g of an, fn, an, fn. So, so the set f naught, f1 is this is a spanning set for the vector space Pn, right? That means this is a basis because we have proved the linearly independentness first, and then we have proved that this is a spanning set. This is a basis of the vector space Pn. So I hope this is the clear. So this is clear. So this is what is the what we have proved here, that this f naught, f1, fn is something like this and all these things. Okay. You know, the point is that here I will give exactly for the next problem is exactly prescribing the value of f naught, f1, fn, and then I mean the next problem, if we keep this problem in mind, the next problem is very easy. Okay. So let's go to the next problem. So this is the problem. What it says, let K be a field and let A naught distinct elements. Okay, you can compare it with the previous questions. Lagrange's polynomial, you can, instead of LK, there was FK, right? Here you can consider LK instead of FK for K equals to 0 to n. So here it is given LKX is equals to product of I naught equals to K, X minus AI by product of I naught equals to K, AK minus AI. So ak minus ai. Okay, for k equals to 0, 1 all the way n. Okay, question is this function k vector space of all polynomials of degree less than equals to n. Moreover, if gx is in Pn is an arbitrary polynomial, then g is the linear combination of this. So if we consider these are very interesting and well known polynomial, these are called Lagrange's polynomial. It is written here, Lagrange's polynomial. So consider in the previous problem, consider Fk is equals to Lk. Then clearly what you can look at Lk at the point Ai, okay, K and Ai, okay. So what will happen? This will be product of I not equals to K, xi minus Ai, okay. Here I'll take Aj. So this will be Aj by product of I not equals to K, Aj minus Ai. So here interesting fact is that you can look at carefully, the denominator is never 0, because denominator is never 0. That's clear because I is not going to be K at any time. Okay, now look at very carefully, what is this value? If I take J is equals to K, 1 second. Yeah, if I take J is equals to, okay, there is a AK, yeah, that's the point. I find how it is changed. AK. If I take J is equals to K, then what will happen? You will replace AJ by AK. In that situation, this is 1. I hope this is very much clear. If J is equals to K. If J not equals to K, that means AJ is something which is not K, AK, okay? But I is running over all the indexes except K. That means AI will sometimes will appear when AI is exactly AJ. So in that situation, it will be 0. So LK polynomial are exactly same polynomial. In the compare this with the previous questions, considering LK as FK. Okay, so that means here LK of AJ is 0 if J not equals to K, and if J, sorry, 0 if J not equals to K and J equals to K at the point 1. So there, if you recall, Fk at the point AI is equals to 0 if I not equals to K. If I is equals to K, it was said non-zero. Nothing has been given, but here it is, we are getting F1. So in that situation, so that means these polynomials are clearly in the previous, it's belongs to the previous class. Thus L0, L1, Ln belong to the previous question, but be careful, in the previous questions this A0, A1, A2 has to be distinct. Okay, let me write it in red so that, okay, this has to be pointed out. Okay, so that means the new problem actually belong to the previous problem with some special condition. Belong to the previous questions. So this belongs to the previous question situation. So this gives this L1, L2, Ln is a basis of the space Pn. But recall that for any G in the space Pn, we have written G as equals to G of A naught by F naught of A naught F1 plus G of A1 by F1 A1. So this is F naught, this is F1 plus all the way G of An by Fn of An and Fn. So main point is that here, so that means in this case G is actually same with G of A naught, but F naught will be replaced by F will be replaced by L. L naught, A naught, L naught plus G of A1 by L1, A1, L1 plus g of an by ln an ln. But note that what we obtained, lk of ak is 1. So that means this is nothing but g naught l naught g1 l1 plus gn ln. So what is the importance of this Lagrange's polynomial? Lagrange's polynomial is, interestingly, if you look at very carefully, that you are giving a function f in the Pn, and you are asked to find that right f in terms of Lagrange's polynomial, linear combination of Lagrange's polynomial. So you know what are the element you need to take the linear combination, but the coefficient you should decide. You should need to decide, right? But the Lagrange beauty of the Lagrange's polynomial is that the coefficients are nothing but evolution of the function f at those distinct points where the Lagrange's polynomial is defined. This is also there. You don't need to calculate all these Lagrange's polynomial or all these coefficients separately. This is very standard. So if you have Lagrange's polynomial at some few corresponding to some prescribed points, of course you want to calculate, you want to obtain degree and polynomial, then you need n plus 1 number of distinct value a naught a1 an in that, and with those values you need to find the Lagrange's polynomial, and then you can write the function f in terms of those Lagrange's polynomial with the coefficients will be look like this way. This is all. Okay. So what are the question in this situation? Yeah, this is what it is. We have proved. This is done then. Question was the polynomial LKX forms a basis of the K vector space Pn, that directly following from the previous question, just to realizing the current situation is aligned with the previous situation with some specific cases. Moreover, if Gx in Pn is an arbitrary polynomial, then G is the linear combination of LKX, and that we have observed. And in fact, the linear combination is given by this specific form only. Okay. I hope this is clear. If still there is any doubt, you can let me ask. You can ask me. I'll try to explain one again. Okay, so I'll give just few seconds only. Sorry. Okay, so let me decide which problem I can discuss in there. Okay, so let me try one more problem. I don't know whether I'll be able to solve or not. If I'm not able to solve, then we'll close, of course, that. So let's this. So this is the Newton polynomial. So question is, the question is actually here. Question is not completely. So question is, K be a field. Okay, and let a naught all distinct point an belongs to K be distinct points. Then Newton polynomial is the polynomial nkx forms a basis of the K vector space Pn, and the polynomial. Okay, this is what it is. This is what it is. The questions. Any part of the question was there? So let me check whether there was any more part of the questions. Just a minute. We call Newton polynomial. These are called Newton polynomials. These polynomials. All these polynomials are used for the computational purposes. So that's why they are relevant. Okay, so I'll not just a minute. So let me just focus on the question. I'll be sticking to these questions whether this is basis or not. I hope this also will follow from the previous problem just to understanding. Yeah, this will also be previous problem. Okay, note that if we consider nk is equals to fk for k is equals to 0, 1 to n to the to one of the previous problem to one of the previous problem of today's discussion. Which previous problem of today's tutorial? Which one? That basically, if you go to this problem here, you have shown that this happens, the linearly independentness and basis and all these things. So, so here it will happen that today's the tutorial, then one of the previous of today's tutorial. So let me know. Then what will happen that nk at the point ai, what will happen, this will be product of I less than k, not that I less than k, not bigger, that x minus ai. This is the thing, x minus ai. So then nk for k equals to 0, 1, 2, n with the convention that, so if I take k is equals to 0, then what is less than of 0? There is nothing. So with the convention that n naught x is equals to 1. Okay, so basically here it is k equals to 1 to n, and this is n naught x equals to 1. This is the convention. Then nk of ai is aj. This is I less than k, aj minus ai. Now look at very carefully. If you take aj is less than equals to ai, I mean j is less than equals to ai, j is less than equals to, basically what is this product, I is running over k, I is running till k, that will be I equals to 0, that means aj minus a0, next will be aj minus a1, all the way aj minus a k minus 1. This is what it is. So if j is strictly less than k, then this is 0, otherwise it is not equals to 0, right? If j is strictly greater than k, then it is not equals to 0, because if j is strictly greater than k, then none of the a naught to a k minus 1, they cannot be equals to aj. Okay, now the point is that, what is the point, I have to prove the linearly independence. Okay, no, this problem is not completely aligned with the those previous problem. So those previous problem, this is not completely aligned, so let's prove the linearly independence. Yeah, this is big problem. Now, moreover, nkx is a polynomial, is a monic polynomial of degree. Okay, why monic polynomial? Because nkx is equals to x minus a naught, x minus a1, all the way x minus ak minus 1. Here is k number of factor, but we can look at the coefficient of x to the power k, that has to be 1, because that coefficient will come when you product x with x with x. All the first term if you product, then I will get x to the power k, and that's the highest degree appearance of the independent variable x in the polynomial. So that's why, and the coefficient is 1, so that's why this is a monic polynomial. So here one can consider, if we consider, here you can consider something like that. If we let's take Pn is a space of polynomials, Then let's take f1, f0, f1. This is constant polynomial. F1 to fn are polynomial of degree of monic polynomial of degree n of degree n. Then these are spanning set basis. Basically this forms a basis. So each fi is polynomial monic polynomial of degree that degree. Okay, just a minute. I have made some little mistakes, so let me. This is not correct. Just 1 second. I mean, basic idea is that suppose you have polynomial something like that, um, a naught. This is the constant polynomial. Then a this is monic polynomial 1. Another is like a naught plus x. Another is like a naught plus a1x plus x square. In this way, if you go, idea is that I just want to make that idea implement in the field. That's what it is I am trying to do. In this, if you go, so then let's, for example, this step. Let's this step. Then this concept plane is this is a basis. This is a basis of P3. How one can prove? Okay. First of all, you can look at carefully. As if I consider this is P naught, this is considered this is F naught, this is F1, this is F2, this is F3. Then what we can write? F1 can be written as A naught F naught plus X. That means X is equals to F1 minus A naught F naught, right? Again, if you write X square, how will write this X square? This can be written as A naught plus A naught F naught into A1 in place of X. If I write F1 minus F naught plus X square, that is equals to F2. That means we can write X2 X square in terms of F2 F naught and F1. Okay, in this way you can write the third equation in this way, like A naught F naught plus A1 instead of X, I will write F1 minus A naught F naught. Instead of A2, I will instead of X square, I will write this full sum F2 minus A naught F naught A naught A1 F1 minus A naught F naught. This is what it is, plus x cube, that is equals to F3. So what will get? X3 is equals to F3 minus A naught F naught minus A1 F1 F naught A naught plus A2. This is also minus F2 minus A naught F naught minus A1 F1 minus A naught F naught. This is what it is. Okay, so this is something lengthy process, but point is that we can write x constant function 1 x square x cube in terms of f0 f1 fn. Thus 1 x square x cube all the way x to the power n can be written as linear combination of f0 f1 all the way fn. if f0, f1, fn are the polynomial of degree n and monic polynomial, okay, then we can write this way. But this is the spanning set of the space of all polynomials of degree n, right? This is a spanning set, in fact basis, spanning set of polynomial of degree less than equals to n. So that gives that f0, f1, fn is a spanning set of polynomial of degree n. So that means if I consider any polynomial Pn n x, that can be written as c0 f0 plus c1 f1 plus all the way cn fn. Now if I consider this is equals to 0, then what I'll get? I'll get a polynomial, and then where you have to prove that c0 cn is equals to 0, we need to prove this, okay? I'll not prove today because I don't have much time. But how to prove this? Because why this will hold, first of all. Why this will hold? This is I'm giving as a task actually, because I don't have time today. So why this will hold? Because if you look at carefully, uh, why Cn has to be 0? Because this is a polynomial. Right now this is a polynomial, and this is, so Fn has x to the power n term, and the coefficient of x to the power n is non-zero. So if we multiply Cn with that, so the coefficient, so whole polynomial, this is a polynomial, and in this polynomial the coefficient of coefficient of x to the power n is actually Cn, right? But if this is 0 polynomial, then Cn has to be equals to 0, right? Once Cn is 0, I can explain. Okay, let me explain this. So just let me explain. So note that f0 is a monic polynomial, that's constant one. F1 is monic polynomial of where the coefficient of x is 1. X square is the monic polynomial coefficient. F2 is the monic polynomial of where the coefficient of x square is 2. In this way, Fn is the monic polynomial where the coefficient of x to the power n is 1. So that means if you consider this is the polynomial, coefficient of x to the power n is Cn. But this is a 0 polynomial. So if this is 0 polynomial, this gives Cn is equals to 0. So once Cn 0, this polynomial reduced to the polynomial, another polynomial, that is c0 f0 plus c1 f1 plus all the way plus cn minus 1 fn minus 1. Right now consider this is equals to 0. Fn minus 1 is a polynomial of degree n minus 1, but monic polynomial of degree n minus 1. So that means in this polynomial, what is the highest power appears? The highest power appears is x to the power n minus 1. And what is the coefficient? That's cn minus 1. But this is a 0 polynomial. So then you will get that cn minus 1. And this will give cn minus 1 equals to. So in this way, we will get c naught is equals to 0. So that's why it is a basis. So this is all for today. If you have any doubt, please ask me. I will try to answer those problems as quick as possible. Otherwise, if you don't have any questions or any doubt, you can leave, and we will meet in the next Friday from 7 p.m. to 9 p.m. if there is not any changes. So if you have any problem, you can, or any doubt, any specific problem you want to discuss, you can send me a mail ID. So send me an email to the mail ID ma21d018@mail.iitm.ac.in. Okay, so you can send a mail to this mail ID. I will discuss those problems in the next. If you don't have any problem, you can leave. I'll close. If you don't ask anything, I'll close this session in next 30 to 40 seconds or 1 minute. Thank you. Yeah.
It's not related to the questions that you have just done, but this is a real question I wanted to ask. That in the exam, it will be pen and paper, I know, but what will be the blueprint of how many questions?
Proof of the questions, I don't know the pattern right now, but I will try to inquire. I mean, we want to know the pattern of the. Basically, you want to know the question pattern in the exam, right?
Yeah, like just in the assignments try to give us, will there be hints or some remarks?
I don't think in exam they will give any hint. Okay, I will try to ask for the collect previous. I will try to ask the about the previous year questions if there is any. If I can by any way, if I can able to find or if I can access, then I will try to say whether there will be hint or not. If there is an explanatory question or whether there will be any explanatory question at all or not. Okay,
Okay, sir. Thank you.
thank you. If you don't have any questions, you can leave.